Thanks, everybody. I've got, as usual, more charts than I should for an 8-minute talk, so I'll be as quick as I can through some of these. Viper, as many of you know, really has two primary goals, and they're listed here. First is to characterize the distribution, and let me reduce that so I can see my screen a little better. Distribution of volatiles and water, especially at the poles, to understand the origin of water. So this is really a fundamental science theme goal. And the other is to provide the necessary data to help begin the evaluation of in situ resources. It's one of the first steps currently on the books in Clive's master scheme. And really it is, I think, going to provide the next great leap in understanding lunar water, because it's going to be mapping at the human scale. And it is truly a mapping mission. And you'll see that in a little bit here. It's not a, its goals, its requirements are built to actually specifically obtain a certain statistical data set so that it's applicable, it can be extrapolated across the entire polar region and vast region, and really understand things in a way we can't right now. Just real quick, this is the Viper rover. It's not a small rover. It's about 430 kilograms. It's solar powered, and that keeps the cost down, but it also, of course, limits its functionality in place and time. Its max speed is about 20 centimeters per second, but when we're in science mode, we're only going 10 centimeters per second. That's to ensure good statistics on the instruments, good signal to noise. It uses stereo imagery, both in and out of sunlight, to understand the hazards ahead of it. It builds stereo maps down to the centimeter scale, out to 8 meters, pretty much continuously. And it's going to go in all environments, everything from full sunlit to full PSR, to make these observations. We're being delivered by one of the Eclipse landers that you heard about earlier. This is the Robotic Lander, shown as an artist rendition here. But even cooler, shown a mock-up here at recently at Glenn Research Center, where we were testing the rover release mechanism and ramps and egress for the rover. That rover there is called the McGrew. It's a full-scale engineering mock-up of the mobility system, just the mobility system of the rover. But I like it because you can see hopefully you can see my mouse. The scale of the rovers, our wheels, these wheels are 50 centimeters in diameter next to a person. We asked for big wheels so we could go over all kinds of obstacles. This is a list of the science instruments. I'll click through these in the sake of time. You've probably heard in the past about the four fundamental instruments, science instruments, which is NIRVIS, the near-infrared spectrometer radiometer imaging system, M-SOLO, a mass spectrometer, and NSS, a neutron spectrometer, and of course our subsurface drill, Trident. Those four you've probably heard about before, but what we've done over the last year is really look beyond those and see what else we have in our toolbox and take the necessary steps to make them science-grade observations. And first are all the cameras. We have the navigation cameras, hazard cameras, we have aft rear viewing stereo cameras. Those we're working with the VIS team, that's the visual imaging team, to make them not just navigation cameras, but truly science cameras. For example, doing all the calibrations, including radiometric, to enable the science that can be done with this great imaging suite. And then more recently than even that, we've really taken a look at the Rover Inertial Measurement Unit, the IMU, with one of our new science co-Is, Kevin Lewis. We are adding extra calibration steps into the flow to turn this into a really excellent subsurface sounding instrument that we can include while driving and drilling. You'll see a little more on that here in a second. So these are the key science measurements and the requirements in terms of the sensitivity, the coverage, vertical coverage, length scales, et cetera. And they're mapped nicely to all of our requirements here. So we are really looking at low water concentrations at level 2, a half weight percent. Many of the instruments go below that. We're sampling we're getting high density sampling across large areas, sampling areas at least 10 to 15%. That's the mapping aspect of this mission. It's not just driving through, looking at one spot and driving on. We have to do our zigzags and get the necessary coverage in an area so we have confidence we've actually mapped the area properly. We have to measure across scales of tens to hundreds of meters. You'll see in a minute, we're driving many, many kilometers. We have to look across both small scales and large scales. We have to have certain sensitivity observations at scales less than 5 meters, actually even less than 10 centimeters in many cases. And we have to sample at multiple depths. So our neutron sample down around 80 centimeters or so. Our drill is a 1 meter drill that we take 10 samples all the way down. And then the new seismic observations that we're using with the IMU can sense down to about 5 meters. So, you know, I'm really excited about that new observation potential there of being able to look beyond what the neutrons can see and what our drill can see. So this captures the kinds of things we're doing while we're driving. And one of the things that I always point out that is most exciting to me about this mission is the instruments are on all the time as best it can be. Obviously the drill, not while driving, but all the other instruments, the NSS, Nervous, M-Solo, the Rover IMU, the cameras, when we're in our non-science driving mode called rails, they are on. When we are in our science mode, they are on. So we are taking data continuously while driving with all these instruments. And then when we stop, we of course drill and prospect down to 1 meter. And that's summarized here. The drilling activity uses a trident drill and goes down in 10 centimeter bites. Each of those bites brings up about 10 centimeters worth of sample, brushes them out onto the surface under the rover. We shield the pile from sunlight. We have sun shades that we position, so it's totally in shadow. And then we observe it with both M-Solo, the mass spectrometer, and Nervous, the near-infrared spectrometer, taking high-resolution images at the same time for each bite. And we've done this at the Glenn Research Center thermovac facility in experiments in the drill tubes, probably about 5 times with both Nervous, Trident, and M-Solo. And it turns out to be a very simple but effective way to profile quite repeatably and accurately water down to concentrations as low as 0.5%. So where are we going? The Viper mission area is an area near Cabeus. Often you hear we're going to Cabeus. No, we're not going to Cabeus. We're going to the mountain plateau just to the west of Cabeus, shown here in the upper right. This mission area is in the process of being named with the, formally, so it will have a formal name eventually here. But it had to meet a number of really critical constraints on the mission. Again, we're solar powered, so we needed sunlight to operate. We're direct to Earth communicating, meaning we're not using a relay satellite. We have to have line of sight to Earth. It needed to have, of course, the trafficability needed to be appropriate. We can drive over slopes of 15 degrees or less. But it also had to have all the proper science criteria, meaning we had to be able to reach a number of thermal environments that we wanted to study. And that's the way we're organized. Our observations is by the thermal environment. So looking in both totally cold places like PSRs, but also warmer places that get temporary sunlight, but in the subsurface temperatures are persistently cold and can retain water. So the site had to have that. This area really offered a lot of opportunities and extended mission periods, which brought down overall mission risk. So that's why it was selected. This just gives another cool view of it. This is actually one of our planning tools. It uses a 1 meter shape from shading DEM, which is built from NAC images. So it really is at the NAC, the DEM is at the NAC resolution, if you will. And what it shows here are what we call ice stability regions. The red regions are areas where it's a PSR, water is stable at the surface. The greenish area, thank you, greenish areas are where it is stable in the top 50 centimeters and yellow in the bottom 50 centimeters of the meter depth. The yellow areas are safe havens. That's where we park when the Earth sets. This just shows a quick analysis from one of our COIs, Caleb Fassett, of the age of the craters in this area. They're all very old, relatively old. The ones we'll be visiting with ages ranging from older than about 3.5 to 3.7 billion years old. This just shows a quick example traverse, short on time, so I won't go into it in too much detail. These are those same PSR areas. Blue shows our traverse, excuse me, as we're driving around over multiple lunar days. Some quick statistics. This is recorded, so you can go back and take a look at these. I'll just call out that the total odometry is about 31 kilometers. We're visiting 32 science stations and making 78 drill sites. That's 78 drillings down to 1 meter. So this is a very productive mission in a short amount of time. And you might have heard that we've moved to 2024, and that we've already begun planning for that, been very busy doing that. This shows an October 2024 start. So we might actually have more opportunity in 2024 than 2023. This shows a traverse that has 5 legs. It starts in October and goes 5 lunar days. This is that mission area I just showed before with those 3 PSRs. In this scenario, we actually visit other PSRs that are many kilometers away. So I'll close there. We're about midway through our replan, given the movement of the launch to 2024. The instruments, though, are full steam ahead. They're getting ready for delivery. The NSS instrument, I think, is packaged and ready to go to Johnson for integration into the rover. We've added a lot of new science team members and are really approaching this as a very robust, full science mission, not just an ISRU mission. And we're ready to go. I'll leave it there. So thank you.